Homework 13, the rational zero theorem, video 1. At the end of the last series of videos, I said that I was going to start a new series of videos for the following, although this could be a continuation of what we saw previously. If you recall previously, we talked about polynomial division, both long division and synthetic division, and we showed how we could use synthetic division to help find the zeros of a polynomial function if we had some advanced information. For example, consider this one in an attempt to answer the question, where are the zeros embedded in polynomials? Let's find all the zeros of the function f of x equals 2x to the third power minus 13x to the second power plus 27x minus 18. And I'll give you a hint. F of 2 equals 0. Now, why is that such a useful hint? Well, if you recall, we had something called the factor theorem from the previous series of videos that talked about the relationship between the factors of a polynomial function and the polynomial function's zeros. For example, in this problem, we know that 2 is a zero of f of x because by definition, a zero is a value that when you insert it into a function produces an output of 0. But the factor theorem says if we know a zero, then we also know a factor. What would the factor be if one of the zeros was 2? The answer is x minus 2. Remember, when we're solving an equation, if it's factored and equal to 0, let's say one of the factors was x minus 2, then we would set x minus 2 equals 0 and solve that to get x equals 2. We're simply reversing the process. We're being told x equals 2 is a solution of this equation, so by moving the 2 back over, it creates one of the factors. And again, the theorem that says zeros and factors occur in pairs is called the factor theorem. If I can spell. So what does this get us? Well, the rest of these blanks are all the same. Since x minus 2 is a factor of f of x, then the function divided by x minus 2 is its cofactor. In other words, anytime we have one factor, there's another factor that goes with it, and you can find it by doing a division problem. So let's do that division problem. Let's do this with synthetic division, since the divisor is x minus a constant. Remember, synthetic division is only good if your divisor is x minus a number or x plus a number. And recall how to set up synthetic division. In the box is the zero of the divisor, which is equivalent to saying it's the opposite of the constant in the divisor. So in the divisor, the constant is negative 2. When we move it into the box, it becomes a positive 2. And the top row of synthetic division are the coefficients of the dividend. In other words, the coefficients in our polynomial function. So from left to right, 2, negative 13, 27, and negative 18. Now, this should have a remainder of 0 because we already know that this is a factor, and if you're a factor, you divide into something evenly. And remember how the steps in synthetic division go. Starting in the first column on the left, you add up its contents. The only number in it is 2, so we'll bring it down. And then you multiply diagonally by the number of the box. 2 times the box number, 2 times 2 is 4. That takes you to the next column, and then you add. Negative 13 plus 4 is negative 9. And then you multiply diagonally by the box number. Negative 9 times 2 is negative 18. Add the next column to get 9. Multiply diagonally by the box number. 9 times 2 is 18. And then when we add the last column, we get a sum of 0, but we were expecting that. And remember that at the end of synthetic division, the bottom row, except for the last number, constitutes the answer to the division problem, the quotient. You just have to put the x's back in, but lower the degree by 1. Since the original function was degree 3, then the quotient will be degree 2. We need to start with x squared. 2x squared minus 9x plus 9, because it's a positive 9. Last number is the remainder. But as we predicted, the remainder was 0. That's what makes you a factor. You divide evenly with no remainder. So what does this get us? Let's go back to the original question. We're trying to find the zeros of this function, which means we're trying to solve this thing equal to 0. The original polynomial was 2x to the third power minus 13x to the second power plus 27x minus 18 is equal to 0. But thanks to the synthetic division problem with the remainder of 0, we can factor this third-degree polynomial. One factor is the divisor, x minus 2. The other factor is the quotient from the synthetic division, 2x squared minus 9x plus 9. We can solve the first factor equal to 0, but it's not telling us anything we didn't already know. X equals 2 is one of our zeros. To solve the other factor, we could get out the quadratic formula, or you could try to factor it further. I believe this will factor. 2x and x will be the first term in each parentheses, a pair of 3's as the last term in each factor, and I believe both will be minus. Give me a second to FOIL it to make sure that it's correct. It is. So one factor is 2x minus 3. If we put that equal to 0 and solve it, we get x equals 3 halves. And the other factor is x minus 3 equals 0. That's easy to solve. We get x equals 3. So we have our zeros. Our zeros are 2. We were given that one. 3 halves. And 3. But the real reason I wanted to do this example wasn't just to do another one like we did at the end of the last video series. It's to try to answer the question, where are the zeros embedded in the polynomial? Because let's face it, I gave you something that set off this chain of events at the very beginning. I told you what one of the zeros was. But what would happen if I didn't give you that? If I had posed the problem without that hint, we would be stuck, because the hint led to a divisor that set up the division problem. If we were not given that hint, we wouldn't know what number to put in there. I guess you could guess randomly, run it through and hope the remainder is 0, but good luck finding that needle in a haystack. But don't worry, all is not lost. You are given a hint even when you're not. What do I mean by that? Well, let's retrace all the zeros all the way back up to the original function to see where they're embedded. Let's start with the 2. Let's retrace where this 2 came from. This 2 previously was a minus 2 in that factor. But where would that minus 2 be recoverable back up here? Well, it would actually show up in a lot of places, but one place is a little easier. If we were to remultiply all of this, this negative 2 would get distributed across all there. And in 2 of those 3 instances, there would be another like term to combine with it, and we would totally lose the 2. But when we multiply it times the 9, that 2 is hiding inside this 18 as a factor. What about the 3? Let's see if we can keep track of where the 3 went. Or rather, where the 3 was embedded in the original function. Let's go to the 3. If we backtrack the 3, prior to unfoiling this, if you will, this 3 was here in this second factor. But if we were to FOIL this out, the 3 would actually get used twice. Once on the outside and once on the last part of FOIL. Well, when we multiply with the outside, it would get combined with the inside product and we would lose sight of the 3. It would be somewhere in here as part of a combined addition and multiplication problem. However, when we multiply the last parts of this FOIL problem, 3 times 3 is 9. So that 3 is embedded inside of that 9 as a factor. And that 9 got hit with this 2 to become the 18. So this 3 is also embedded in the 18. So I think what you might start seeing now is that the constant term at the end of a polynomial function contains a lot of information about what might be a 0. Well, let's track one more. Let's track the 3/2. This one it's not trickier to follow, there's just more to keep up with. Looking for a green marker, not sure if I have one. Let's see if it works. It doesn't write a lick. Oh, got rejected by the pencil sharpener. Let's try this green marker. A little bit better. Let's keep track of this 3/2. We'll keep track of the 3 with the blue circle and the 2 with the green circle. So if we backtrack where the 3/2 came from, the 3 was the constant term in that factor, whereas the 2 was the coefficient of the x. And if we keep backtracking, well, this 3 as part of the last part of FOIL gets hidden inside of that 9, but where's the easiest place to find the 2? And the answer is as part of the first part of FOIL. The 2 is embedded here. I mean, it's point blank a 2, but it's also embedded as a factor of 2. Well, we already know that this 9 goes back to the 18. Where can we recover this 2? Well, if we were to remultiply all of this, the very first term in each factor would multiply to make this 2x cubed. So it seems like the numerator of this fraction was also embedded in the 18, whereas the denominator of this fraction was embedded in the 2 up front. So when I say you're not given a hint about what a 0 could be, about what could possibly create a factor, or what could possibly go into the box, that's not entirely true. Because every 0, either as a whole number or as a fraction, its pieces are embedded back in the original problem. In the next video, we'll make this a little bit more specific instead of just hand-wavy, and we'll talk about something called the rational 0 theorem, which will answer the question, if you don't give me a number to put in the box in synthetic division, where should I look?